Fires in buildings cause over £80 million worth of damage every year in Britain. Most of this damage occurs in old buildings, such as this group of warehouses in Bradford. In this fire, 3 large warehouse groups and several smaller buildings were completely destroyed in less than 4 hours. Extensive damage such as this can easily occur in old buildings put up in the days when little thought was given to the effects of fire. Today, much more is known about structural fire protection, and a building can and should be designed to withstand a fire without suffering structural collapse. This gives an opportunity for all the occupants to leave the burning building and for some of its contents to be moved, and for firefighting to begin in time to prevent its complete destruction. To make this possible, the main structural elements of the building must withstand the effects of fire without serious distortion or loss of strength. They must have an adequate fire resistance. The term fire resistance here means the length of time a structural element will withstand heating under standard conditions. Building regulations and bylaws specify the fire resistance requirements for various types of buildings. They range from half an hour for small houses and flats up to 4 hours for large warehouses, for which the highest grade of fire resistance is required, since they would contain large quantities of combustible material and could have much more severe fires. Concrete beams are widely used in the construction of large buildings, and it is important that they shall have an adequate fire resistance. Although concrete won't burn, it loses strength when it gets hot, and gravel concretes spoil away from the surfaces during fire. A fire that occurred while this building was under construction caused the concrete to spoil away from the corners of the beams, exposing the reinforcing steel. Concrete also spoiled away from the ceiling. Once the steel is exposed to fire, its temperature can rise sharply. Collapse could have occurred if the fire had continued, since steel loses its strength when it gets hot, as is shown by the bending and twisting of unprotected steelwork in a fierce fire. So, if concrete beams are to have a good fire resistance, the concrete cover must remain in place around the reinforcing steel as long as possible. The Building Research Station has carried out an investigation of the fire resistance of concrete beams in cooperation with the Fire Research Station, to find out the performance of different beams designed to serve the same purpose. The beams tested included concrete-encased steel beams, reinforced concrete beams, pre-stressed concrete beams with pre-tensioned wires, and pre-stressed concrete beams with post-tensioned cables. Some of the beams were provided with supplementary reinforcement in the cover to hold the concrete in place around the tensile reinforcement as long as possible, and thus to protect it from the heat. Tests show that concrete beams are likely to fail when the steel attains critical temperatures, which for reinforcing steels are around 550 degrees centigrade, and for pre-stressing tendons around 400 degrees. Since the steel temperature is so important, arrangements were made to measure it by fixing thermocouples to the main tensile reinforcement in each beam. The beams were made at the Building Research Station under carefully controlled conditions. Most of them were made with sand and gravel aggregates to give a crushing strength of 6,000 pounds per square inch at 28 days. Some beams, however, were made with lightweight aggregates. After curing under standard conditions, the beams were taken to the Fire Research Station, where a special furnace had been built for carrying out fire resistance tests on beams under load. In this furnace, the test beam was supported at both ends by a steel frame enclosed in the fire brick walls. The load was applied at 4 points of the span by 2 loading beams bearing on the test beam through steel rollers. 2 hydraulic jacks applied loads to the center of each loading beam. The deflection of the beam was shown on a dial, and a brick pier was built to support the beam after failure. The beam and its loading system were built into the furnace, which was heated by gas burners closely spaced along both sides. Now let's see the real thing. Here is the furnace with the covers removed, ready to receive the beam. When it is placed in position, the beam forms part of the furnace roof. Its bottom and sides are exposed to the heat just as they would be in a fire in a building. Since the top surface remains outside the furnace, the load can easily be applied to it through the two loading beams and the steel rollers. The rollers bear on steel plates that are bedded onto the beam. The loading frames are constructed so that they can be installed easily, for they have to be dismantled after each test to allow the test beam to be removed. The pin joints connect them to the steel frame in the furnace walls that support the ends of the beam. The hydraulic jacks are connected by flexible pipes to the hydraulic pump and load indicator. Before the test begins, a load equivalent to the total design load is applied to the beam. This load is maintained throughout the test. When the preparations are complete, the gas burners on both sides of the furnace are lit. The furnace doors are closed and the test begins. The temperatures in the furnace and in various parts of the beam are recorded throughout the test, thus providing time temperature curves for the furnace and for the steel reinforcement. The furnace temperature is raised at a standard rate which is specified in the British Standard for Fire Tests. Evaporation of the water in the concrete occurs at an early stage in the test. It takes place along the whole length of the beam. Spy holes at each end of the furnace enable the beam to be observed. We can see one row of burners, the brick arch covering the exit flue, and the bottom and one side of the beam under test. Thermocouples hang from the furnace roof alongside the beam. A cine camera at the other spy hole photographs the beam during each test. It's protected from the radiant heat by an aluminium shield and by a supplementary shutter in front of the lens, which opens just before the camera shutter. One picture was taken every 5 seconds throughout the test. We will now see 3 typical tests. First, a beam made with gravel aggregate without any supplementary reinforcement. The concrete began to spool away from the surface early in the test, eventually leaving very little cover to the steel reinforcement. The steel soon became hot. After an hour and a quarter, it reached a temperature of 400 degrees centigrade. After only an hour and a half, the beam failed. Next, a test on another gravel concrete beam, this time with a cage of supplementary reinforcement to hold the concrete in place. In this test, no external lights were provided, and the beam was photographed solely by light emitted from the hot brickwork of the furnace and the beam itself. Everything was cool at the beginning of the test, so there wasn't enough light to see the beam. But as the temperature rose, the beam and the furnace interior became visible, glowing dull red at first and gradually getting brighter. Not much damage was done to the beam during the first hour, but after that, pieces of concrete began spalling away from the arises. They left black patches on the surface of the beam, but these soon glowed red as they heated up to the temperature of their environment. The supplementary reinforcement retained the major part of the concrete cover in place. The concrete protected the steel from the heat of the furnace and thus delayed its temperature rise. After 2 hours, it was only 200 degrees centigrade, although the furnace temperature was over 1,000. So far, the beam had retained its strength and had deflected only slightly. During the next 2 hours, very little more concrete spalled away, but the deflection increased. After 4 hours, the steel temperature was still only 330 degrees, although the furnace temperature had risen to 1125. The beam was still in good condition and the deflection was not excessive. The beam had successfully withstood the heating conditions, and when the test was discontinued, it still sustained the load, although the deflection was then quite considerable. Next, a test on a beam made with lightweight aggregate. Concrete made with lightweight aggregate is generally not liable to spall when exposed to a high temperature. After 1 hour, no spalling had taken place and hardly any deflection was apparent. Lightweight concretes have a lower heat conductivity than the denser concrete made with gravel aggregate. This delays the temperature rise of the steel for a longer time. In this test, after 2 hours, it rose only to 150 degrees, compared with 200 degrees for the gravel concrete beam. The beam continued to bear the test load satisfactorily, and after 4 hours, no surface damage could be seen, and the deflection had increased only slightly. The beam had easily provided a fire resistance of 4 hours without any supplementary reinforcement. The use of lightweight aggregate will thus provide very good fire resistance, but its cost is usually higher than that of gravel aggregate. Many similar tests were carried out on beams with various methods of reinforcement. The results obtained all followed the same pattern. They showed that if concrete cover to the reinforcement could be retained in position and it was of adequate thickness, then the beam could stand the severe heating conditions in the test without failure. When the concrete cover broke up, the steel temperature rose rapidly and the beam failed. The time temperature records show the degree of protection given to the steel by each form of construction. Let's compare the records for the 3 tests we've just seen. This curve shows the furnace temperature, which rose at the standard rate in each test. The black curves represent the steel temperature. In the first test, the steel had a cover of 2.5 inches of gravel concrete. This spalled away fairly quickly, so that the steel temperature rose to 400 degrees in only an hour and a quarter, and the beam failed after an hour and a half. In the second test, supplementary reinforcement was provided. This held the concrete in place and protected the main reinforcing steel, so that its temperature rose more slowly. After 2 hours, it reached only 200, and after 4 hours, only 340 degrees. This beam did not fail. The third test showed that the use of fire-resisting lightweight aggregate provided still better protection. The steel temperature rose even more slowly. After 2 hours, it reached only 150, and after 4 hours, only 280 degrees. Again, the beam satisfactorily withstood the test. These 3 tests are typical of a much larger number of similar tests carried out at the Fire Research Station. They show quite clearly that the fire resistance of concrete beams can be greatly increased by the addition of supplementary reinforcement or by the use of lightweight aggregate. Thus, with suitable design and construction, concrete beams can meet the building regulations and bylaw requirements for any type of building. And this is true for all types of pre-stressed concrete beams, as well as for those with ordinary steel reinforcement. For houses, flats, and office buildings, the fire resistance requirements vary from half an hour to 2 hours. The tests have shown that these requirements can be satisfied with ordinary reinforced concrete beams. For storage buildings, which are likely to contain larger quantities of combustible materials and to have more severe fires, the fire resistance requirements may be as high as 4 hours. The tests have shown that in these cases, reinforced concrete should be provided with supplementary reinforcement. This reinforcement may be omitted if the concrete is made with a lightweight aggregate. Research of this nature has shown the way to reduce the annual loss due to fire by suitable design of modern buildings. Further information may be obtained from the Fire Research Station or from the Building Research Station.